This conference will now be recorded.
Hello everyone. Last day we have seen three properties of sulfuric acid, and those are, if we just have a look in the previous slide: acidic character, dehydrating property, low volatility. Now dehydrating property, it is actually the property that it can absorb water, and actual example also we have seen. Here we have some equations: formic acid, glucose, ethanol, and copper sulfate 5H2O. But now we will see the picture of this experiment. We have taken concentrated sulfuric acid and sucrose. So when we are adding it, that is at time 0 second, there is presence of, that is we are just adding the concentrated sulfuric acid. And in the second beaker, we have added dilute sulfuric acid. Okay, that is the difference. In the first one, it is concentrated. In the second one, it is dilute. Now after 15 seconds, see, now there is visible change appearing in the concentrated H2SO4 beaker, but not in the dilute H2SO4 beaker. Okay, so here why we are getting this type of black mass, it is because of the formation of carbon. Remember the reaction, that is this one. Here 6 carbon and water molecules will be removed. So this, because of this carbon formation, here we are getting this type of black mass. But the dilute H2SO4 beaker, that is the second beaker, see, there is no change. Okay, so it proves that only concentrated sulfuric acid can absorb water, but not dilute sulfuric acid. Fine. Concentrated sulfuric acid, it actually produces nascent oxygen. Now we are discussing the oxidizing property, number 4 property. Okay, and H2SO3. See, when H2SO4, it is producing H2SO3 and nascent oxygen, that means atomic oxygen, then this nascent oxygen is actually responsible for this oxidizing property. Now we will see some reactions where it is showing oxidizing property. Hot concentrated sulfuric acid, it is moderately strong oxidizing agent. That is, if we compare the oxidizing property with phosphoric acid and nitric acid, then sulfuric acid, it comes in between. That is maximum oxidizing property by nitric acid, then sulfuric acid, and then phosphoric acid. Okay, so this is the order of oxidizing property. That is, we are comparing the oxidizing property with two other acids. Both metals and non-metals can be oxidized by concentrated sulfuric acid, and the fate of sulfuric acid is that it will be reduced to SO2 because it is acting as oxidizing agent, so it will be itself reduced. Copper, when reacting with H2SO4, here copper is forming copper sulfate, and H2SO4, that is actually converted to SO2. So this is one of the oxidation reaction. Here oxidation state is +6, here it is +4, that means it has gained electron. Second equation, reaction with sulfur. From 0 oxidation state, now we are having +4. So if we compare oxidation state with respect to sulfur, from 0 now we have +4, that means it has lost electron. So this is oxidation. But if you compare with respect to H2SO4, that is a sulfur present in H2SO4, its oxidation state is +6. So with respect to H2SO4, from +6 to +4, this is gain of electron. So H2SO4 is reduced to sulfur dioxide, but sulfur is oxidized to sulfur dioxide. Third reaction, now this is non-metal, because both metal and non-metals can react. So here we have example of metal, copper, then sulfur and carbon, non-metal. So carbon is oxidized to carbon dioxide. From 0 oxidation state, it is now +4, and H2SO4 is reduced to SO2. The last equation, HI, that means it is I minus, H plus I minus, iodide ion, but after reaction now it is iodine, that means 0 oxidation state. So I minus from -1 oxidation state, now it is 0 oxidation state, so this is loss of electron. And H2SO4, it is again converted to SO2. So all these 4 reactions, these are actually showing that sulfuric acid, it has oxidizing property, but not in dilute condition. When it is in concentrated condition, then only it can show oxidizing property. So is there any doubt in this slide? Sulfuric acid, as it has wide applicability. Okay, it can react with almost so many different types of chemical compounds. So that is why it is also called king of chemicals. Fertilizers like ammonium sulfate, that is NH4 2SO4, superphosphate. So in all these fertilizers, you can see there is presence of sulfate ion, and that is the sulfur, it is coming from H2SO. So fertilizer, when we are trying to synthesize, then we can take the help of H2SO. Then the formation of dyes, pigments, paints, explosive, for example, trinitro-toluene. Okay, and storage batteries. In storage batteries, there is also presence of concentrated H2SO. Remember, in electrochemistry, we have already discussed about it. There are two types of batteries. Some batteries we can recharge, some batteries are not rechargeable. So the rechargeable battery, the most common example is inverter that we use at our home. There is presence of concentrated sulfuric acid. In synthesis of imperative chemicals like hydrochloric acid, phosphoric acid, nitric acid, sodium carbonate, all these can be synthesized with the help of H2SO4. Then metallurgical application that we have seen in metallurgy chapter, it is utilized as a part of refining of petroleum, as pickling agent and laboratory agent. It has huge application because it has different types of property: oxidizing property, dehydrating property. In organic chemistry also, this dehydrating property, it is utilized highly. Here we have a question that H2SO4 is oxidizing only when it is in hot condition and concentrated, because if you take dilute and cold, it will not work. So why it is so, that we will see here. Suppose you have zinc, and when you are adding to it dilute H2SO4, there is formation of hydrogen gas. So when it comes in contact with dilute sulfuric acid, then there is liberation of H2, and this, it is just the same reaction as it does with hydrochloric acid. So suppose you have taken hydrochloric acid instead of H2SO4, same type of reaction you can see. Now there is formation of ZnCl2, and again H2 is liberated. So this is actually the properties of acid. So here HCl and H2SO4, these two acids are showing their acidic property, because we know that acid, they can liberate, that is, metals can liberate hydrogen from the acid. So here you can see hydrogen is liberated in both cases. So this reaction is not the reaction example of reaction where it is showing oxidizing property. Okay, so dilute H2SO4 is not showing oxidizing property, it is simply showing its acidic property, that we have also seen in case of other acid. For example, here as I have written this equation. But when it is heated with concentrated sulfuric acid, then the latter is reduced to sulfur dioxide. So here oxidation state of sulfur is +6, this is also +6. So no change in oxidation state. But if you consider the second reaction, now it is +6 and this is +4. Here there is no change, but this is gain of electron. That means it is acting as oxidizing agent and it is gaining electron from zinc, and that is why zinc is now Zn2+, that is in salt form. So remember, you can see the difference in these two reactions. So when it is dilute, there is zinc sulfate is formed in both cases, but the other product is different. You can get generation of hydrogen is possible, that is only when it is dilute H2SO4, but when it is concentrated, we are getting different side product. Now it is sulfur dioxide and water. Okay. So remember, it will show oxidizing property only when it is hot and concentrated, not just in any condition. Any doubt? So regarding different properties of H2SO4, we have problems here. And remember, it is multiple correct choice. That means if there are 4 options, more than one option will be correct. The question is the reaction in which concentrated H2SO4 is acting as oxidizing agent. So you have total 4 reactions here, but all the 4 reactions are not example of oxidizing reaction property. Some reactions among these 4 where H2SO4 is acting as oxidizing agent, and we have to find those options. The first reaction, this reaction we have just seen in the previous slide. Remember, Hi, that is iodide, Hi minus, that is converted to 0. So this is loss of electron, and H2SO4 itself is reduced from +6 to +4. So the first option, that is actually showing its oxidizing property. The second reaction, we have taken sodium chloride salt. Now sodium chloride in presence of H2SO4, there is simply exchange of this ion. See, Cl minus, now it is replaced by HSO4 minus, and Cl, it is attached now with H. So this is basically displacement of anion, that is HSO4, it is moving from H2SO4 towards sodium, and chloride is moving from sodium chloride to H2SO4. So see, oxidation state, that is also not changed because chloride is present before reaction and after reaction. In both sides, chloride is having -1 charge. So this is not oxidation reaction. So this is not correct option. Third equation, calcium fluoride H2SO4. Now calcium fluoride, here you have calcium ion and 2 fluoride ion, and we have H2SO4. So this is also simply exchange of ion. Just take this sulfate. So you will get calcium sulfate, right? And HF. So you will get 2 HF. So this is also displacement. And F is having -1 oxidation state, both in the left hand side and right hand side. So no change in oxidation state. And sulfur also, it is having same oxidation state. This is +6. This is also +6. So this is not example of oxidation reaction. Then come to the last one. See, this reaction we have seen in the when we have discussed the question that why only concentrated and hot H2SO4 can show oxidizing property. And remember, it can react with copper, but different product generation is there. Copper sulfate will be formed. Sorry, that example was with zinc, not with copper, but it is actually analog. That is same type of reaction. So copper is converted to copper sulfate, fine. But see, here if you look at H2SO4, it is +6 here, it is also +6, but SO2 is also generated. It is not simply liberation of H2. So here H2SO4, it is not acting as acid. It is acting as oxidizing agent because sulfur is having now oxidation state +4. Okay, so there is change in oxidation state, it has gained electron, because whenever it is showing oxidizing property, it will be itself converted to that is reduced to sulfur dioxide. That is the fate of H2SO4. Whenever it is showing oxidizing property, its fate is that it will be reduced to SO2. So the last reaction is also example of oxidizing reaction. So correct option will be 1 and 4. Okay. Next problem. Here we have some reactions that are unbalanced. Zn, zinc, reaction with hot concentrated H2SO4, there is formation of G, R and X. Remember this reaction we have seen in the last slide, right? Then the second reaction, this is number 1. Zn when reacting with concentrated sodium hydroxide, there is formation of T and Q, another 2 product. And the third reaction, now G, which is one of the product that is obtained in the first reaction, now it is reacting with hydrogen sulfide and ammonium hydroxide. And we are getting Z, which is basically a precipitate. That information is given. Other 2 products are also generated, and one of these product is also generated in the first equation. Now we have total 4 options and more than one option will be correct. So that is why here it is mentioned option or options. That is one question may be one option may be correct or more than one may also be correct. The first statement is saying that oxidation state of Zn in T, that means in this compound, it is +1. But see, it is very easy to understand that even if you do not know that what are the products T and Q, suppose you do not know, then also you can answer this option, whether this option is correct or not. Because Zn having oxidation state +1, this is highly unlikely. Okay, so even if you do not know T, then also just apply common sense that +1 oxidation state of Zn is not possible. So this statement cannot be correct. And if we actually want to know what is the product T, it is actually when Zn reacts with NaOH, it forms a sodium zincate, Na2ZnO2. Okay, so when it is Na2ZnO2, it is basically 2Na plus and ZnO2 minus. This is carrying 2 negative charge. So here oxidation state of Zn is basically +2, not +1. So if it is mentioned +2, then only it is correct. So this is not correct option. And the next one is bond order of Q. That is the other product. That is 1 in its ground state. So this is T, and other product is basically, see here Zn is reacting with NaOH, it is forming Na2ZnO2, and hydrogen is also produced. Now hydrogen, if we write it in this way, there is only one bond present between two hydrogen, and that is number of bond is nothing but bond order. Suppose if there are 3 bonds, just take the example of acetylene, that is 3 bonds are present between CC, it is triple bond. So in that case, you will say that bond order is 3. But here only one bond, so bond order is 1. So this statement, that is Q is 1, bond order having 1 in its ground state, that is under normal condition. So this is Q. So this statement is also correct because bond order is 1. Now come to this one. Z is dirty white in color. But to understand what is Z, we have to know what is G. Otherwise, we will not be able to understand what is Z. So to understand Z, now we have to write this equation. Now Zn when reacts with hot concentrated H2SO4, then H2SO4 will act as oxidizing agent. And it will produce Zn sulfate. And remember, whenever H2SO4 is showing oxidizing property, its fate is it will be converted to SO2. So among these 3 products, one of the product must be SO2. Another product will be zinc sulfate because the metal salt will always be produced. And the third product is water. Now see all these reactions. G, that is one of the product, as I have said, it is ZnSO4, sulfur dioxide and water. Now if you are thinking that why not G is SO2 and ZnSO4 is R. Now that you can write. But see here G is reacting with H2S and ammonium hydroxide and it is producing ZXY. But if you are thinking that G is SO2 or water, but SO2 and water will not react with H2S and NH4OH and it will produce this type of products. It is possible only when ZnSO4 is present. That means ZnSO4 must be G. Okay, so if ZnSO4 is Z, that means SO2 and H2O, one of them will be R, another one will be X. So ZnSO4, how it reacts with H2S and NH4OH, that we have to know, otherwise we will not be able to understand what is this precipitate. So this is actually dirty white precipitate, zinc sulfide, and XY, that is 2 other products are also obtained. And see, here water is produced, so this X, it is water, it must be H2O because here SO2 is not generated. So X cannot be SO2, X must be H2. So the third statement that Z is dirty white in color, this is also correct. And the fourth statement, R is V-shaped molecule. Now R is SO2 and SO2 is having this type of structure, lone pair. You can also write the structure like this. But in any case, it is actually bent, that is V-shaped like this. So as it is V-shaped, this statement is also correct. And even by mistake also, if you are choosing R as water, suppose you have written R is water, in that case also this statement is right, because water, this is actually tetrahedral, but without lone pair, the ultimate shape is like V, inverted V. So that is why if you, even if you by mistake considering it as R, then also it will be correct. So except A, all the other statements are correct. That is B, C, D. These three options are correct. Fine. So is there any doubt in these two problems? Should I repeat it once more? So that is the end of group 16, and now we are entering the last group, which is sorry, not last group, because after this there is group 18 also. So this is group 17. So group 17, we collectively call them as halogens. Okay, general term. Now, what is the origin of this term? The Greek word halo means salt, and gens means bond. That means they are salt producer. That is, from this halogen you can get some salt. For example, you can use chlorine and you will get sodium chloride salt or sodium bromide salt like this. So as they are used for salt production, so that is why their names are halogens. Now if we look at the compound, look at the elements down the group, first fluorine, the first member, then chlorine, bromine, iodine, astatine, and tennessine. Now the last one, it is synthetic, so mostly we do not discuss it. And remember, this is radioactive also, which is clear from this picture. Now HCl, Br, the first four elements we mostly discuss here, as we have reached almost at the right hand side of the periodic table, because group 18 is the last group, that is the rightmost, but 17 is just before that, so we are almost at the end. And we know that whenever we move from left hand side to right hand side in the periodic table, non-metallic property increases. So as we are almost at the right hand side, you can see non-metal, it is purple, denoted by purple color. So all these are actually non-metals. Though it is true that down the group metallic nature increases. That is, if we are asked that whether F will be more non-metallic or astatine will be more non-metallic. Obviously, fluorine is more non-metallic. Astatine will be more metallic because down the group metallic nature increases. But these are actually not metal. Fine. And mostly our discussion will be restricted up to iodine. So here from the color we can understand that up to iodine all are non-metal, and these two, they are also radioactive, but only though two colors are not possible to show simultaneously, so only one color is shown. But remember, they are radioactive. Okay, and this one, it is synthetic. It is not natural presence is not there. The halogens are highly reactive non-metallic elements. Now, why they are highly reactive? Because if you consider their electronic configuration, general electronic configuration, it is NH2NP5. So just one electron is less, so that it can reach the inert gas configuration NH2NP6. That means it is searching for one electron. Okay, it is highly interested in one electron, so that after gaining that one electron it can achieve inert gas configuration. So that is why it is highly reactive, and you will hardly see halogens occurring as in free condition, because they are so reactive, they cannot remain in free state. They will always remain in compound. That is, for example, if you consider chlorine, it will mostly try to remain as Cl minus, not chlorine gas. Because when it is Cl minus, it has already gained one more electron and it has reached inert gas configuration. Okay, so halogens are highly reactive, and you can find some similarity with the S block elements, because S block elements that are present in the left hand side of the periodic table, where we have seen that they are also very reactive, especially group 1 metals. They are very reactive. Why they are very reactive? Because their general electronic configuration is ns1. So if they can somehow lose this electron, they will reach the noble gas configuration. So they are eager to donate this electron, and halogens, they are eager to accept this electron. So that is why reaction between S block elements and halogens, it occurs very easily. Okay, and ionic compounds are formed because the metals completely donated the electron, and non-metals that they have accepted the electron completely. So that is why we write Na plus Cl minus. It is not covalent bond. That is, electrons are not shared between them. Sodium already given one electron completely, and chlorine accepted that electron completely. The elements of group 17 show great similarity among themselves. That is, if you compare with other groups, just compare the groups 15 or 16 that we have discussed, just finished group 16. There is some discrepancy in their properties, especially the first element, it behaves differently. But in this case, you will see some great similarity. That is, some consistent nature is there. And this type of similarity is also observed in case of S block elements, that is group 1 and group 2. There is regular gradation in their physical and chemical properties. Okay, so for example, if you are considering acidic property, there will be gradual decrease or increase. That is, it is not inconsistent, that suddenly there is any break and it is not gradual. It is not like this. There is a smooth decrease or smooth increase. So that is why it is mentioned there is great similarity among themselves in some properties. Occurrence. Halogens are present in combined form because they are very reactive. That is why they cannot remain in free state. They will always remain in some compound. The first element, fluorine, exists broadly as insoluble fluoride. For example, cryolite Na3LF6. This is insoluble compound. Then fluorspar, calcium fluoride, fluoroapatite, CA5PO4O3F. And among these, the primary source of fluorine is fluorspar, that is calcium fluoride. Little amount of fluorine element that is also available in soil, plants of stream water, and bones and teeth of creatures. This is a natural occurrence for fluorine. Come to the next two, that is chlorine and bromine. They are available in ocean water in the form of chloride or bromide salt of metals. Metal means group 1 and 2 metals. Sodium, potassium group 1, magnesium, calcium group 2. And the most common compound is sodium chloride. That is ocean water, it comprises around 2.5% by weight of sodium chloride. So you can understand that this salt is present mostly compared to the other salts. Now, some more points related to occurrence we will see in this slide also. The dry beds of ocean additionally contains vast stores of sodium chloride alongside little extent of calcium chloride and carnallite. So calcium chloride, that is CaCl2, and carnallite is actually this type of composition, that is KCl, MgCl2, 6-1. Now iodide, that is the fourth element, they are found in trace amount in ocean water in the form of salt, because it is mentioned iodide, not iodine. And primary source of iodine is ocean weeds, some sea fishes, and the next element, that is astatine, it has radioactive property. And the next one, that is number 6, tennessine, it is actually synthetic radioactive element. And you can understand from the half-life value, millisecond. So you can understand that how unstable it is. Half-life means that is the time in which it will be 50% disintegrated. That is, it will be converted to some other element. That is the radioactivity property. Okay, so within millisecond, second is very small, and millisecond you can understand is how small it is. So within millisecond, it will be 50% disintegrated. So it's highly unstable. Okay, so that is why our discussion will be restricted up to iodine, not astatine or TNS. Electronic configuration. So general configuration is NH2 NP5 after noble gas, and fluorine is from second period. So after helium, this is the configuration, and we know in second period there is no d orbital. Then in third period, after neon, that is atomic number 10, 7 more electron, because chlorine is having atomic number 17. So this is also falling NH2 NP5. But here we have vacant 3D. It is not that we do not have any D. We have D, but that is not filled. This is vacant. Then in case of bromine, when it is fourth period, there will be, this is the general configuration. But before that, we also have 3D10, because now 3D is present and it is completely filled. So because of this presence of 10D electrons, which you do not have in case of chlorine, there will be some difference in properties. That is, if we compare properties of chlorine and bromine, there will be some difference. Then the next one, fifth period. So that is why valence shell configuration is 5s2 5p5, but we will also have 4d10. So here also we have 10d electrons. And in case of astatine, there is also, which is from 6th period. So this part is common, NH2NP5, but we have not just d electrons, we also have 14f electrons, because this is from 6th period. And before that, there are all the lanthanide elements, so that is why already 14f electrons are present. So as there is f electrons present, that is when you are moving from iodine to astatine, there is additional f electrons. So because of this f electrons also, there will be difference in properties, because when we know that screening property of f and d electrons are very poor, especially f is more poor if we compare with d. So because of this poor screening effect, there will be direct effect on the chemical properties. We will see that later. But right now, this is the electronic configuration. Remember, the first two, there is no d electron, and in fact, in the first element fluorine, there is no d orbital. In chlorine, there is d orbital, but it is vacant. In case of bromine iodine, there is fully filled d electrons, 10 d electrons, that is fully filled d orbitals. And in case of astatine, you have 14 f electrons and 10 d electrons. As these elements require one electron, that is one extra electron, it is required to achieve stable octet or closest ideal gas configuration. So that is why they have strong inclination to either increase one electron by forming ionic bond, that you have already seen in case of NaCl, because sodium, it has lost electron, because sodium having atomic number 11. So when it has lost electron, minus electron, that electron is gained by chlorine and its atomic number is 17. And after accepting electron, now it is achieving Cl minus, that means now there will be total 18 electrons. Noble gas configuration is achieved. So this is ionic bond formation. So it can achieve stable octet, that is 8 electron in outermost shell, either by forming ionic bond where it has completely accepted the electron, or it can also form some covalent bond. And we know that in covalent bond there is sharing of electron. It is not that one element completely given electron, another one completely accepted that. It is simply sharing. And that you can, for example, you can take the example of HCl. It is true that Cl is more electronegative. So that is why the electrons that are present between H and Cl, one is given by H, another one is given by Cl. But Cl is more electronegative, so there will be, that is the electron density, it will be closer towards chlorine. But that doesn't mean that it is not covalent. It is covalent bond because there is sharing of electrons. Though the polarity is, that is negative charges towards chlorine, but it is covalent bond. So in this case, chlorine is having total 7 valence electron, right? So 7, this is electron in red color, that is from chlorine, and 6 more electron in the form of lone pair. So surrounding chlorine, there are 8 electrons. 7 its own electrons, and 1 electron it is coming from hydrogen. So now it is having stable octet, that is a fully filled octet. So either by sharing electron or by accepting electron completely from other element, that is ionic bond, it can achieve stable octet. The halogens constitute the most reactive group of nonmetals, because now we are at the right hand side extreme. And group 18, they are not actually, we do not say that they are non-metals or that, because they are so inert in nature, they do not take part. But just before the last group, that is the previous group, I mean to say group 17, that is halogens, as there is deficiency of one electron, so that is why they are highly reactive. They have a tendency to accept one more electron. High reactivity of halogens is because of their strong inclination to pick up electron, that is ionic bond, or share an electron, that means covalent. Okay, so in this slide, is there any doubt? Now we will see their trend is chemical, atomic properties. Atomic properties means atomic or ionic radii, then ionization enthalpy, electron affinity, etc. Atomic and ionic radii. So atomic radii, when it has not gained or accepted electron, that is, it is Cl. But if it is Cl minus, now we will, it is ion. So now the size, when we will discuss, we call them as ionic radii. It is no longer atomic radii. Okay. But whatever it is, that is, even if it is, suppose all of these elements are in ionic form, then it is F minus, Cl minus, Br minus, or all of them are in atomic form. Okay. In both cases, whenever you are moving down the group, there is increase because of extra added quantum shell, that is principal quantum number is increasing. So ionic and atomic radii increases from fluorine to iodine because of the increase in their number of quantum shell. Okay. Now halogens have the smallest radii in their respective period. Period means when, suppose you have considered second period, and when it is second period, the last element, that is boron, carbon, nitrogen, oxygen, fluorine, the last element, that is fluorine, that will have smallest atomic radii. So gradually, when you are moving from left hand side to right hand side, the size is decreasing. So it will have smallest atomic radii in respective period. So you cannot compare a second period elements with the third period. Okay, because there is change in quantum shell. So when you are comparing along the period, you have to consider in same period. Then only comparison is possible. So when you are in the same period, you are moving from left to right, they will have, that is halogens will have smallest size. And it is because of the maximum effective nuclear charge. Because when you are moving from left to right, there is decrease in size, and the nucleus that will have, that is positive charge that will be felt by the outermost electron, that will be very high. That is the effective nuclear charge. But if we are moving down the group, that is from fluorine to chlorine to bromine, like this, there will be increase in quantum shell, and that is why you can see here we have size in picometer in the y-axis, 0 picometer, 20 picometer, 40, and this is F, Cl, Br, I, S. Now there is increase, though one thing is noticeable here, that the first difference, that is the difference between F and Cl. See, this is 40. Chlorine is around 60. So the difference is 20 picometer. But when you are moving from chlorine to bromine, it is around, that is 60 something. Okay. And it is 80 something. So now the difference, though it is not very easy to understand from this picture, but remember the first jump, when you will actually see the values in picometer, the first jump is, that is the gap is very high. But as you are considering the other gaps, especially see the gap between iodine and asteroid is very low. because of additional 14F electrons, because their screening property is very poor, so that is why nucleus will have positive charge for the outermost electron, size will decrease. So because of addition of quantum shell, there is increase in size, but there is also a opposite factor operating here, which is this poor screening property of d and f electrons. So that is why the expected increase is not there. Increase is there, but expected increase is not there. Now next is ionization enthalpy, another atomic property. So ionization enthalpy is the amount of energy required to remove the most loosely held outermost electron, that is valence electron, in their gaseous state. Now when you are moving the electron very easily, that means you are not providing very high amount of energy. That means we will say ionization enthalpy is very low. So they have very high ionization enthalpy as compared because of the small size as compared to other groups. Now other groups, if we consider group suppose 1, then 2, then there is D block, then group 13, 14, 15, 16. So as we are moving from left to right along the period, so if you are considering any particular period, so here we have taken sodium, magnesium, aluminium, that means it is third period. So in third period, as we are moving from left hand side to right hand side, it is true that there is no regular increase or decrease. But one thing is very clear from this graph, that maximum value, that is for fluorine. Just compare with all the other. We are not comparing here variation, that is smooth variation is present or not. We are just checking that which one is having maximum ionization. So they will have very high ionization enthalpy because their size is smallest. Remember what we have mentioned here in the first point of atomic radii, ionic radii, that because of the increasing number of, sorry, this point, not this one, second point, halogens have the smallest atomic radii in their respective period. So in the third period, Cl will have lowest size. So that is why you cannot remove the outermost electron very easily, because the electron is very close to nucleus. So you have to provide more energy. So see here the value is around 1600 kilojoule per mole. Okay. But when you are moving down, due to increase in atomic size, obviously ionization enthalpy will decrease. And that is common observation for other groups also. But again the same thing, as just compare with the size factor. In the size, what we have seen, when you are moving from F to Cl, there is big difference. That means size is highly increased. So when you are considering the ionization enthalpy, it will have the reverse effect. Because when size is very high, ionization enthalpy is less. When size is small, ionization enthalpy is very high. That is, it is inversely related to each other. So as fluorine is having lowest size, so that is why here ionization energy is maximum. Okay. Similarly, when it is chlorine, ionization energy is summer. Here, see the first jump, the gap is very high, but though there is gradual decrease, but still these gaps are not very high. And this is because of the presence of D and F electrons, their poor screening property. Fine. So is there any doubt in this slide? Third atomic property, electronegativity. So electronegativity, if we compare, see, we have taken the Pauling scale values of electronegativity because there are different scales for electronegativity. Mostly we take the Pauling scale that we have taken here in Y, and in X-axis all the elements are present. So fluorine is the most electronegative element. Its electronegativity is around 4. And fluorine is not just the most electronegative element in group 17, but it is also the most electronegative in the whole periodic table. Okay. These elements are highly electronegative, and electronegativity decreases down the group, because when we are moving down the group from F to Cl to Br and so on, metallic properties increase. That means electronegativity will decrease. And if you consider respective period, just consider the previous example, that is the green graph. So in this particular period, maximum electronegativity, that will be for chlorine. Okay. So that is mentioned here. And see, here Pauling scale values are given. So it will be, this is for chlorine, this is for argon. Okay, so chlorine has maximum electronegativity, which is around 3 point something. Here also it is 3 point something. After electronegativity, the next property is electron affinity. Now, electronegativity, electron affinity, though at a first glance it seems almost same thing, but actually they are completely different. Electronegativity, what it is? It is the tendency to draw electron density towards it. So suppose there is a bond between X and Y. X is giving one electron and Y is giving another electron. Okay. Now, if X is more electronegative than Y, then the electron density that will be closer towards X. Okay, so negative charge will be developed, minus del plus del. So this property is actually electronegativity, capacity to draw electron. Fine, but electron affinity is completely different. Electron affinity is just the reverse process of ionization enthalpy. In ionization enthalpy, you are removing electron, and for that you have to provide some energy. But here, what you are doing, you are adding one electron forcefully. So here also some energy will be released, and mostly the values of electronegativity, they are negative. Okay, because energy is released. Halogens have the most negative electron gain enthalpy. It is also called electron affinity in the respective period. So if you consider this third period from sodium, magnesium, aluminium, then chlorine will have maximum electron affinity. Now when we are saying maximum electron affinity, it is actually highly negative value. So suppose there is minus 20, one value, another value is minus 10. So if this is for element A, this is for element B. That is the minus 20 is the electron affinity value for the element A, minus 10 is for B. Now here we will say that A is having more electron affinity than B. So basically we are focusing only on the numerical value. So in case of A, minus 20 kilojoule energy is liberated. But in case of B, minus 10 kilojoule energy is liberated. That means lesser amount of energy liberated. So that is why we will say electron affinity of A is greater than B. Okay. Electron gain enthalpy turns out to be the less negative on moving down the group. That means it is becoming less negative. So suppose if you are moving down the group from it is minus 20, then minus 10, then minus 5. That means gradually it is becoming less negative. So what we will say, down the group, electron gain enthalpy is decreasing. Don't think that it is considering the negatives. Okay. So here we have the graph for all this, and see here gradual increase is not present. Maximum electron affinity is for chlorine. See, this value is maximum. When you are moving towards down the group, it is decreasing, and also when from Cl to F, it is decreasing. So maximum is for chlorine. So see here, numerical value it is maximum for chlorine. Negative sign is always there because it is released energy. But why this discrepancy is present, that we have to know. We can expect that fluorine should have the maximum electron affinity, but that is not the case. Now what happens here, when there is atom fluorine, there is already have some electron density, 2s2 2p5. Now its size is very small compared to chlorine. Its size is comparatively larger. So when you are adding one electron forcefully, there is already some electrons present. So electron density is very high because same number of electrons present in smaller volume, but that is 7 electron present here. Here also total 7 valence electron, that is in case of chlorine, but volume is high. That means electron density is high in case of fluorine. So when electron density is high and you are adding one more electron forcefully, obviously the process will be difficult. It is not very easy. because there will be electron-electron repulsion. But as here electron density in case of chlorine, it is not so high, you can comparatively, you can add the electron easily. So that is why here this process is facile, but in case of fluorine, the process is not facile, so lesser amount of energy will be released here. This is the reason for discrepancy. So strong inter-electronic repulsion in the relatively small 2p orbitals of fluorine, because this is from second period. There will be repulsion. It will lead to less negative electron gain enthalpy of fluorine. So when the value is less negative, it means the process is not so facile. So in case of astatine, it is having the least negative value, -270. That means as we are moving down, metallic property is very high. So when you are trying to add electron here, one more electron, it has no tendency to accept it. Okay, so that is why the process is not very facile. And when the process is not occurring very easily, energy release that will be less. Okay, so this is a trend for electron affinity. And this question is very common, that why fluorine is having the maximum electron gain enthalpy, because our normal expected trend is not present here, and that is because of the high electron density of fluorine. So one more electron when you are trying to add, that is not very, it will not very occur very easily. Okay, so is there any doubt in these two properties? Now we will see some physical properties, that is boiling point, color, physical state, melting point, all these are physical properties. So see, if you look at this table, fluorine is yellowish in color, chlorine is greenish, and bromine orange brown, then iodine purple. And under normal condition, the physical state, the first two are actually gaseous in nature. Bromine is liquid if you are considering normal condition, that is at room temperature, and iodine is solid. So gradually as we are moving down, mass is increasing, so obviously from gaseous state now it is moving to liquid state and then solid state. And look at the melting point values. Down the group it is increasing, and that is expected, because when it is in gaseous condition, melting point will be negative. In degree centigrade unit it is negative, but when it is solid it will be positive. And down the group, increase in NP and BP, that is melting point, boiling point, this is natural. And the logic is that down the group, atomic mass increases, van der Waals interaction increases. To overcome van der Waals interaction, we have to provide more energy. So that is why when you are converting it from liquid state, from solid state to liquid state, that is the melting point. That means you have to provide more energy. And in case of boiling point, that is from liquid state to gaseous state, here also down the group it is increasing, so you have to provide more energy, because van der Waals force increases with atomic mass. So see here, we can observe some smooth variation in their physical properties. As we have mentioned in the first slide, remember that we can observe some smooth variation in their properties. Very less amount of discrepancy we will find. And this type of smooth increase or decrease we have also seen in case of S block elements. All halogens are colored. Now we have not talked about color in other elements, that is the other groups. In some cases we have mentioned it, but here you can see all these four elements, there is specific color, and it is because of absorption of radiation in the visible region. Because if it is in other region, UV or IR, then we will not be able to see color. But in this case, all the wavelength for absorption, it falls in the visible region. Bromine and iodine, these two elements, they are sparingly soluble in water. That is, water solubility is not good. We have mentioned only bromine and iodine. That means in case of fluorine and chlorine, they are hardly soluble. That is, down the group, water solubility, though all are very poor, having poor solubility in water. But still, if we want to compare relative solubility order, then down the group it is increasing. So that is why bromine and iodine, these two are, they have some solubility, but not the other two, F and C. But if you take some organic solvent, like chloroform, carbon tetrachloride, carbon disulfide, hydrocarbon, like for example cyclohexane, hydrocarbon. So all these solvents are very good for their solubility. Now see, fluorine, when it is in gaseous state, it is pale yellow, but when it is in liquid state, this is also yellow, but it is slightly intense. Chlorine gas, there is a slight difference. Fluorine is yellow, but now there is a greenish tinge. Okay, some greenish appearance is also there. This is the liquid form. Bromine, when it is in gaseous state, is orange brown or deep yellow, whatever you say. And when it is in liquid state, this is the color, brown. And see, some vapors are also appearing just above the surface. Iodine, when it is in gaseous state, this is the color. And when it is in solid state, this picture, when you are looking from distance, it seems as if they are black solid. But actually it is not black. It is deep, intense purple. But it is so intense, it appears as black. But actually it is not black. Fine. Here we have three solutions. This is for chlorine, this is for bromine, this is for iodine. Now see, as chlorine, it has no solubility in water. So it is almost clear water. But bromine, it has some solubility, so some color you can see. Iodine also, it has some solubility. And solubility is comparatively more. That is, compared to bromine, it is more. And here, the previous picture that you have seen, it is only water. But now the picture that you are seeing, here we have added cyclohexane. So there is non-polar solvent or any other hydrocarbon solvent we have added. In this case, we have added cyclohexane. So now both cyclohexane, that is non-polar solvent, as well as polar solvent, water is present. Now water layer is this. This part is water layer. That is, the lower level is water. And as solubility in organic solvent is high, and so when you will add hydrocarbon solvent, that is organic solvent, and if you are shaking the test tube and you are keeping it for some time, there will be layer separation. And you can see this part is more clear, but this part there is some chlorine present. So all the chlorine, now it is moving towards the organic solvent. All the bromine is now in organic part and all the iodine in organic part. So it proves that solubility in organic solvent is high compared to water. So that is why, and we know that non-polar solvent, polar solvent, they do not mix with each other. So that is why you are able to see two different layers. And in the organic layer, it is solid, which is clear from the picture. So regarding all the slides, is there any doubt? We will end the session here. Thank you for listening.